So today I will talk about universal K-matrix and fuse K operators. This is a joint work with Pascal Badeillac and Atelier. And actually, this is a generalization of the work done by Appel-Vlaar last week. Okay, so in quantum integral systems, one goal is to obtain the R-matrix, which is a solution of the Yang-Baxter equation. So this one. And for instance, the easiest case, let's say for J1 equal J2 equal 1/2, you have the XXZ R matrix, which is given by this 4x4 matrix. And we will always assume here that Q is different from 0 and it's not a root of unity. Okay, so more generally, you can obtain solution of the Yang-Baxter equation by simply, yeah. So you can obtain solution of the Yang-Baxter equation through evaluation of a universal R matrix. So it's an element in H times H. More precisely, it is in a completion of H times H, where H is a Hopf algebra, and it satisfies three axioms. So the first one is R delta equal delta of R. It just intertwines the coproducts. And the last two axioms tell you how delta acts on the leg of the universal R matrix. And together, these axioms imply that the universal R matrix satisfies the universal Yang-Baxter equation. So we say that it is universal because it has the same form, R12, R13, and R23, but it lies in H times H times H. So it's an operator. Okay, so now consider the example of the Hopf algebra UQSL2 affine. And in the 90s, Koroshkin and Tolstoy gave an explicit formula for such universal R matrix. Consider the positive root systems of SL2 affine and the root vectors of UQSL2 affine are given by this expression here. So the universal R matrix take this factorized form with explicitly given, and actually you can evaluate explicitly this expression because everything here is known. So introduce the evaluation map from UQSL2 affine from UQSL2 and the finite dimension representation pi j of u from UQSL2 affine to some matrix with a spectral parameter u. And from this universal R matrix, through evaluation, you obtain L operators and R matrices. And this is what we use in quantum integral systems. So actually, there is another example of quadratic algebra, which is called the reflection algebra. So for R solution of the Yang-Baxter equation, you have the so-called reflection equation given by this form, RK, where where K is given by this form. So it's a 2J plus 1 square matrix whose entry are some series in U with coefficient KABJN. So KABJN can be either scalars. In this case, we talk about K matrices, or it can be some elements in the comodule algebra B. And in this case, we talk about K operators. So you can notice here that a more general reflection equation is given by, instead of having this RJ1, J2 here, you have some R21, J2, J1. So here we simply consider the p-symmetric R matrices. Okay, so as an example of this reflection equation, consider the R matrix given previously, which is called also the XXZ R matrix. And the more generic solution for this equation for J1 equal J2 equal 1/2 is given by this matrix here, where epsilon plus minus, K plus minus are some scalars, different from 0. Okay, so here we may wonder, if we can make something quite similar with the universal K matrix, with the universal R matrix, that is, can we define some universal K matrix such that after evaluation we obtain K operators, and again after another evaluation we get K matrices. And also, what could be the related quantum integral models associated to these K operators and matrices? So there is In recent years, there was advances in this direction. In particular, there were Balagovic, Kolb, and Appel and Vlaar who work on this subject. In 2019, Balagovic and Kolb introduced some universal K-matrix in H, the Hopf algebra, so a one-leg universal K-matrix, and they managed to obtain some constant K-matrix. So the reflection equation does not have any spectral parameter. 1 year later, Kolb alone defined some two-legs universal K-matrix in B times H, where B here is a right co-ideal subalgebra. And doing so, he obtained a reflection equation without spectral parameter to get constant K matrices, K operators, sorry, so without any spectral parameter. And as seen last Friday, Appel and Vlaar here define some universal K matrix in one leg, so that they obtain K matrices with spectral parameters. Okay, so here we have several goals. We want to define a universal K matrix in B times H, so a two-legs one, but here B would be some comodule algebra. Then we want to construct some K operators for any spin J that satisfies obviously the reflection equation, so this one. And we will consider in particular the case B equal AQ, which is the alternating central extension of the qOnsager algebra. And we will give some relation with the universal K matrix here. And finally, we want to see what application can be done with the T relation and what are the related spin chains for these models. Okay, so actually we got three results. So we have a definition of a universal K matrix K in B times H for B a right comodule algebra. And through evaluation for irreducible representation, we obtain some K operators and K matrices for a reflection equation with spectral parameter. Then we will construct fused K operators, the Kj of U, using a so-called fusion procedure that solves the reflection equation, and we'll give supporting evidences on the existence of such universal K matrix here. And finally, we will see that assuming that this universal K matrix exists, the T relation can be directly shown. Then we'll see some specialization to open spin chains. Okay, so before defining the universal K matrix, we need to give some elements. So the first one is B, a right comodule algebra over H. So it has a coaction map from B to B times H, the Hopf algebra, that satisfies two relations, the co-associativity and the co-unity. Secondly, we will need a Drinfeld twist. It's an element in H times H that satisfies these two relations. And finally, we will need a twist pair, which is a datum of an algebra automorphism psi of H, and the Drinfeld twist given here. So the twist pair needs to satisfy these two relations. That tells you actually that if you have a universal R-matrix, you often call it as a quasi-triangular Hopf algebra. That is, you have some universal R-matrix R with a delta. So you can twist this R and delta by either J or psi. And what this twist pair tells you is that these two deformations must coincide at the end. So now we'll give some example for each definition. So consider H equal UQSL2 affine and B equal AQ, the alternating central extension of the qOnsager algebra. This is the right comodule algebra. For the twist pair, if you take J equal R21 inverse, or J equal Wattons 1, the trivial twist, then they satisfy these relations. And now for the twist pair, if you take eta and the trivial twist, it is a twist pair where eta acts on the root vectors of UQSL2 affine as follows. Okay, so we'll keep this example for the next slide. Okay, so now we have everything to define the universal K matrix. So for H, a Hopf algebra, and B, a right comodule algebra, and psi j, a twist pair, we say that K in B times H is universal K matrix if these three axioms are satisfied. So the first one is similar to the universal R matrix. It's K delta B equal delta psi BK. Here, delta psi is some twisted coaction. And the last two relation tells you how the coaction delta acts on the leg B, the first one, and how the coproduct delta acts on. Okay, so having these three axioms, you can show that they imply the universal reflection equation, which is of the form KRKR. Okay, so now let us see some special cases. So the first one is if you fix the twist pair as psi equal identity and j equal R21 inverse, so it's a twist pair, and this relation K1, K3 reduces to the universal K matrix defined in the work of Balagovic and Kolb. The second special case is if now you no longer consider B to be a right comodule algebra, but it should be some coideal subalgebra over H, then, and some any twist pair, then you apply the counit on the axioms here so that it kills the B, and you get the universal K matrix in Appel and Vlaar, so the one defined Friday. Okay, so we have our definition, and now we may wonder, okay, can we make some evaluation to recover the usual reflection equation? So for this, now we will fix the twist pair psi j equal eta and a trivial one, and we define some K operators as an evaluation of the universal K matrix. So identity times pi j U inverse. And the evaluation of the universal I matrix leads to the usual R matrices, as follows: pi times pi of R. So now fixing this twist pair, you take the universal reflection equation and you take this evaluation map here, and you find that you obtain the usual reflection equation, the one that we were looking for. So now a question is, okay, so here I didn't give any expression for the universal K matrix. I don't even know if it exists, but can we construct some solutions of this equation here, some Kj of u? And the answer is this. For this is a fusion procedure. Okay, so first, our goal is to construct explicit expressions for the fused K operators. And to do so, we will need some inspiration with this universal K matrix. So fix psi j as follows: eta and identity, and some b. So at the end, we will find that Kj of u is written in terms of f, e, and k and r. So on the left, you have some Kj, and on the right, you have lower spin K matrices, K operators. So F and E are actually intertwiners. It means that for us, E will solve such equation. So it means that when E acts on a pi j representation of any element in UQSL2 affine, and when it goes from the left to the right, it splits this part into a pi 1/2 times pi j minus 1/2 with a delta. And it fixes also these u1 and u2 parameters. So in generic, you can put any u1 and u2, and in order to have this relation true, it will impose you some ratio upon this spectral parameter as follows, the red part. And F here will be a pseudo inverse of E, that is Fe equal 1. Okay, so this is how we define our intertwiners. Now recall the K3 axioms, the last one, and we can make some evaluation for this axiom. In particular, if you apply this map here, identity times pi, then the right-hand side becomes only this part, K2 R K1. And finally, in order to obtain this proposition here, you need to combine both evaluation and the intertwiner property. That is, you simply inject some fe equal 1 and you make it pass from both sides. And then you get this formula. So in the following slide, we will not longer assume that k exists, and we will construct some fuse k operators simply using these intertwiners f and e here. And we'll consider the case for b equal aq, the alternating central extension of the qOnsager algebra. So before giving the fuse k operators, we need to define what is this algebra aq. So it is the alternating central extension of the qOnsager algebra, and it has three representations. The first one is called the compact. The second one is the Greenfeld type, and the third one is the reflection equation type. And it is this one we will be interested in. Okay, so AQ has these generators, W minus K, W K plus 1, JK plus 1, and J tilde. So now, for convenience, we introduce some generating functions, the W plus minus and G plus minus of U. We define the AQ algebra through the reflection equation algebra. So you have, as usual, the RK equation. R here is the XXZ R matrix given at the beginning, and the K operator here it has this form. So it's linear in the currents, W plus minus U and G plus minus of U. And this is a representation of this AQ algebra. Okay, so now our goal is to obtain some higher spin K operators, that is K operators of this form, but for instance, a 3×3 matrix. So to do so, we defined, okay, now I recall that we do not assume the existence of K, and we define our fuse K operators as follows. So here, you have the same, in some way, the same structure, which is F, K, R, K, E, where F and E are the intertwiners given 2 slides ago. And we can show by induction that these fused K operators satisfy the reflection equation, the generic one, with any J1 and J2. Okay, so the only thing I didn't give here is that you get some analogous formula for the RJ1, J2, using also these F and E. So inserting everything, you can show by induction that it holds. Okay, so for instance, for J equal 1, you have this operator here, K1, which is now, okay, for K for 1/2, it was linear in the currents, and now it becomes quadratic. It's J plus, J minus, etc. And F and E takes this easy form. So now we want to compare the ball Kj of U coming from the universal K matrix with the fuse Kj coming just by just by fusion. Okay. So recall that for the universal R matrix, through evaluation, you get L operators and R matrices. So actually, we can do the same. That is, we can relate these R matrices coming from the universal R matrix to the one coming just by fusion formula. So I didn't give you these formulas, but they are similar with the F and E. And actually, these two R matrices are related simply by a scalar here, the pi J1 mu J. And we may wonder if there is some analogous result for the K matrix, the K operator. So recall that ball Kj of U is the evaluation of the universal K matrix, and the calligraphic K is obtained by fusion. So we want to find some relation between both. And actually, we have some conjecture about it. So it is this one, the red part. So if, okay, the conjecture is that the ball Kj and the calligraphic J are related by some central element mu J of U. And we also need some additional properties, additional equation on the nu. and the evaluated coaction on this new. Okay, so why is it conjecture? Because actually, okay, first, we don't know existence of universal Kmatrix, but we know that if it exists, so it is defined by these three axioms, then an evaluation of these axioms should give three equations satisfied by this ball kj. So it is where we stop. And on the other end, having constructed these use kj operators, we can actually prove analogs of these evaluated axioms, the ki prime. And now, if you impose this conjecture here, you can show that these equations here imply that the ki prime are satisfied too. So in that sense, it gives supporting evidences on the existence of k. Okay, so finally, we will discuss the relation to open spin chains.
Guillaume, we started a little bit late, so we have 3-4 minutes still, but just a reminder.
So, okay, so we have the AQ algebra. You have a map phi that goes from AQ to AQn, which is some elements in UQSL 2 times n. And now, in order to look at the related integrable models, you need to look at the transfer matrix T here. So it's a trace of k plus times k, and it can be written in terms of this I to k plus 1, where this I to k plus 1 are some linear operators in terms of the generators of AQ. So now to get the Hamiltonian, you need to take the logarithm derivative of the transfer matrix. So it's an element here in AQ. Then you apply this phi so that you have an element in UQSL 2 times n. And now you apply some finite dimensional representation of UQSL2. And then you obtain the usual spin 1/2 XXZ open spin chains. So one thing that we may wonder here is that how can we construct Tj of U in terms only of the I to k plus 1, in terms of these generators? So the answer is the Tj relations. So assume the conjecture and assume that universal K matrix. So the conjecture tells you that ball kj equals some central elements times the fuse k operators. Then we can show that the Tj relation is directly satisfied. Okay, I will skip this. So now for specialization, consider the transfer matrix for any spin j. So trace k plus j times fuse k ju. You apply phi so that it's an element in UQSL2 times n. And now applying some fine dimensional representation for all the UQSL2 copies, you get this usual standard form, which is k plus product of r, k minus, and product of r. And now specializing this ji, you can obtain, for instance, if everything is equal to spin 1, you obtain the usual XXZ spin 1 open boundary condition. If you fix everything to j, then you obtain the spin chain for spin j open boundary conditions, and also the alternating spin chain. So a consequence of this Tj relation is that you obtain Tj of U in AQ as a polynomial of total degree 2j in the I to k plus 1, and the Tjn of U in AQn will be some polynomial of degree 4jn in W0n and W1n, the generators of the quotient of qOnsager. And here's some summary and perspective. So I think I can stop here and I'll let you give me some questions. So thank you for your attention.
Thank you. Thank you. Any question from audience here or online? Well, I have a short question. I mean, I think most of this was for UQSL2, so, right? I mean, but I remember that for example, higher rank cases, even when you don't go to algebraic abstraction, what you have, even concrete classification of concrete matrices is still ongoing. Is this correct? So can you comment a little bit of higher rank cases?
Okay, I don't know very much about this. Yeah, I don't know what to say about this.
Other questions, maybe? Well, if not, then thanks, Guillaume, the speaker again.